A situation we've got to be a little bit careful of, and that often comes up in these transition matrix questions, is if you get a more complicated recurrence relation to work with. So if you ever have something that's in the form that tells you that S of n plus 1 equals t times S of n, so that part's kind of the same as what we just looked at, but then with a matrix that's being added or sometimes subtracted at the end, in these situations you can't use that sort of power method that we just applied. You have to work step by step. Okay, so if you need to find out the value after, like, if you need to find S3, you have to go S1, then S2, then S3. Okay, you have to work step by step in these situations. So continuing on with this factory example, we're saying the factory regularly buys new machines, and so maybe a more accurate rule for describing the state of these machines is going to be given by Sn plus 1 equals T times Sn plus R. So we've got this situation where we're going to be adding a matrix at every step. We still have the same transition matrix, but R is represented by this matrix 3, 2. Essentially what's going to happen is we're going to be adding in 3 operating machines and 2 broken machines every day, right? Maybe the factory's picking them up from some other factory or something like that, who knows. So on the initial day, 80 machines are operating and 20 are broken. Using the above rule, how many machines are in operation and how many are broken after 3 days? So we need to work out S3, right? But as we said, we're going to have to do this step by step. So let's get S1 first. S1 will equal T times S0 plus R, right? And all those things are defined already in the question. So let's calculate it. Let's go T times S0. So again, just using some copy pasting because we were doing this question already. So T times S0 plus the matrix R. Oops, it's not a fraction, it's a matrix. Okay, 72, 33. That's our matrix for S1. All right, which is saying that after 1 day, we've got 72 operating and 33 broken. You can see these numbers don't add up to 100 anymore because we've just introduced 5 new machines, right? So they now add up to 105. Okay, we're trying to get to S3, remember? So S2 will equal T times S1 plus R. All right, so we're just working through step by step on the calculator. Again, multiplying by the transition matrix, it's T times S1 plus R. You can see how lazy I'm being with copy and pasting, but it saves you time, so always try to save time instead of typing matrices that you've already entered. All right, there are our values for S2, 65.85 and 44.15. All right, and then S3 equals T times S2 plus R. And so we just got to repeat the process one more time. So T times S2, which we just worked out there, plus that matrix 3, 2, and there we go. 61.18 and 53.82. All right, remember the labels on this was first number's operating, second number was broken. So again, answer the question directly. Therefore, after 3 days, we have, to the nearest whole number, 61 operating machines and 54 broken. All right, so a little bit trickier there when you have a relationship like that with a matrix being added at each step. You've got to work step by step. We can't use a power to sort of jump ahead there. All right, and a couple more just sort of tricky cases to be aware of. Sometimes you'll get a question where you don't actually know the matrix S0, so you're not given the initial state matrix, but you might know some other value, some other matrix, you know, in the sequence. You can still work out future states using this. You just really have to think about how many more steps into the future you want to work. So for example, if you wanted to work out the state matrix S9, you could do that by calculating the transition matrix to the power of 4 times the state matrix S5, because to get from S5 to S9, you just have to multiply by the transition matrix 4 times, right? And you can also be asked to work backwards to find a previous state. And to do that, what we're really doing is taking our recurrence relation, if we ever have to work backwards, if that's the sort of standard recurrence relation, to work backwards, what you would do is if you were trying to rearrange the equation so you could go the other way, you would actually multiply both sides by the inverse of t and end up with this equation here. So you can actually use the inverse of a transition matrix to go backwards by one step, right, and get Sn, so the previous state, would equal t to the power of -1 times the next state. Okay, so that's a bit of a tricky one. Let's have a look at how this works with a specific example, and hopefully this will clarify things. So in this question, we're given the matrix T, a transition matrix. We're given the state matrix K5, and we're also told that Kn plus 1 equals T times Kn. So we've got a more standard kind of transition matrix equation here. So first thing we're asked to find is K7. K7 is just 2 steps ahead of K5, right? It's 2 more states into the future. So you can say that K7 will equal T squared times K5. All right, so we're going to put in the transition matrix into our calculator. It's just trying to get that so you can see the question and the calculator. So 0.6, 0.4, 0.3 and 0.7 to the power of 2 times the column matrix K5, which was 80, 90. And we get 73.5 and 96.5. Now this question, the matrix is our final answer, because this question is just asking us to find the matrix K7. It's not a situation like before where we have to say, you know, this many operating machines and this many broken machines. The answer is just the matrix, because that's what the question was asking us for. Okay, and in part B, determine K4. Well, this is the tricky one, right? Because K4 is actually the step before K5. So it's a situation where we're having to work backwards, and that's where we can use the transition matrix, or the inverse of the transition matrix, I should say. So K4 will equal the transition matrix to the power of -1 times K5, right? If we want to go backwards here, we're really just rearranging the matrix equation as was written up here. So again, save time, use what you've got in your calculator already. We're copying down the transition matrix, this time to the power of -1. That makes it the inverse, multiplied by K5, which was that 80, 90. And we get the matrix K4. Right, which is 96.6667. Technically speaking, we shouldn't round answers unless we're told to, so let's write that as 96 and 2/3, and this can be 73 and 1/3. Write them as mixed numbers there, because then they're not rounded off. Right. Okay, so a few tricky ones in that section. Obviously, do your best to keep working through your checklist exercises, but if these examples are making you a little bit confused, or the questions from the checklist giving you some grief, make sure you contact your teacher and ask them for help. Bye for now.